Let's do it.
All right. Thank you. So I started playing around with a little compiler project recently. And along the way, I've been spending a lot of time revisiting some rather foundational computer science topics just to get an efficient enough implementation for something I'm working on. And so I guess I'll just kind of dive straight in by diving, like, here's a Lambda calculus, right? We have variables, we have applications, and we have lambdas. And then lambdas are binding an extra variable. That's what the maybe is doing for me here. And we can build a monad for it that does capture avoiding substitution. It avoids the bound variables. If you want to see a more advanced version of this, you can go use my bound library. But I think, how many people here are not familiar with the Lambda calculus? All right. Ooh, wow, there's hands. Sorry. So what I'm interested in doing right now is I'm going to be talking a bit about compiling this down to a more primitive form where I'm not dealing with names. Okay? And this goes way back. And what we're going to do is we're going to compile down into combinators. And so what is a combinator? A combinator is basically just a function that has no free variables. So there's a fairly small set of combinators that have been used historically that go back to a guy named Moses Schoenfinkel or Mosai Ilyich Scheinfinkel. It got transliterated from Russian to German, and then he went back to Russia and went crazy. And then died in a sanitarium, and then people burned all his papers for heat. But he's the guy who gave us the idea of compiling, the idea of using combinators for evaluating code. So if we look at, so Moses Schoenfinkel is the guy on the top of the list there. Then his work was picked up by a guy named Haskell Curry. Some people might have heard of him. They named a language after him. And then David Turner built up on the work that had gone before and came up with a more efficient version of compiling from that toy Lambda calculus that I was just sketching into combinators. Okay, and so he built a language called Sasel, which started out as a strict language in 1972-ish, and then he rewrote it into a lazy language in 1976. And then the work that he was doing on that evolved into a language called Miranda, which is the precursor to Haskell as we know it today. So Sasel was an untyped language, and Haskell was is a typed language. We haven't killed it yet. And so that, I'm just kind of giving a list of references for combinators if you're interested in exploring. There's a book by Smolyan on Tamaka Mockingbird, which kind of gives a huge pile of puzzles in this form. And there's this other paper here by Sabine Broda and Damas that does a much better overview than I'm going to do today about summarizing historical results about trying to improve the asymptotic performance of compiling to combinators. All right, so in the same sense as we just built a little Lambda calculus, we'll build a little logic. Here we have variables, the applications of a combinatory logic term to a combinatory logic term, and then S, K, I, B, C, all these funny names. And if you're not familiar with these names, we actually are reasonably familiar with them in Haskell, but under different names. So S takes X and Y and then a Z and then passes Z to both sides. This is app in the reader monad. KXY gives back X. It's just const. I is id. B of XYZ is X of Y of Z. We recognize that as function composition, just dot. C XYZ is X ZY, it's flip. And then Y of F is fix of F. So these are the names that we use. And there's a relatively, slightly, it's not as straightforward as you would like, algorithm for compiling from the Lambda calculus down into this combinatory logic, so LC to CL in the kind of terms that I've established here for the names of the data types. That goes back to Schoenfinkel in the 20s, which is called bracket abstraction or abstraction elimination. And here, basically, the idea is if I want to compile a variable, I get back a variable. If I compile an application, just walk down both sides. When I want to compile lambdas, I have to be a little bit more careful. So if you're looking at lambda XX, that's the identity. If you're looking at lambda XY, where Y isn't X, then you're going to get K of a variable. And then, so it's basically const of a variable. And then a bunch of stuff for S, and then we've got C's and B's and K's. You don't need to have C and B. They're slight optimizations of writing in terms of S and K. You don't even need I, and you don't need Y. You can get away with just S and K. But in practical terms, we tend to use a larger combinatory basis. Okay. Oh, and many Haskellers today are already aware of this stuff because they use point-free notation. They start with a function that has a lambda, and they say they don't really want the lambda, and they either by hand spot that they can replace it with a function composition, or they hand it to @pl on LambdaBot, or they go to this point-free IO website that Tony introduced me to the other day, which turns around, you can just paste in a Haskell expression, and it will remove all the lambdas from it. And what it's secretly doing is this algorithm that goes back to Schoenfinkel, and it's just, instead of calling them S, C, B, and K, they're just using the names that we know. Okay, so this is the idea of abstraction elimination. And the algorithm that's given here is actually, when you take a term from the lambda calculus and you spit out a term in combinatory logic, it can blow up by a factor of O(n) to the third, O(n) cubed. And there's a Turner's work, which I'm not going to show here, adds a few more combinators that gets it down to O(n) squared. Okay? And then the world took a different direction. So in 1979 was that last paper from Turner, and then John Hughes wrote a paper in 1982, right before he finished his PhD, on what he called supercombinators. And the idea of supercombinators, which was a bit in the air at the time, was the idea of building a set of combinators that is specific to your program instead of working with a fixed set of SKI, BCY, right? If you're going to be appending lists a lot, it makes sense to build an append combinator that does the thing, because if you do all the work to manipulate SKs and Is and stuff like that, you're doing a lot of administrative constructing and tearing apart of these apps of different data constructors, or different combinators. Okay, and in general, at the risk of grossly oversimplifying, it was probably about a 40% speed up at the time. And then Leonard wrote a paper on his compiler for LazyML, which took John Hughes's approach and pushed on it further. He said, how can we efficiently build these supercombinators? And he wrote them by basically building a little bytecode for a small imperative language that implemented the supercombinators. And this was sort of the roadmap forward that we followed ever since. Since then, Simon Peyton-Jones gave the paper on the spineless tagless G machine, which is the approach that we use in GHC, which is an evolution of Leonard's approach. And then we improved the performance of this further by spotting opportunities for dynamic pointer tagging inside of Haskell, which is to make it so that we use the least significant few bits of a pointer to tell you which data constructor it is, so that we can avoid randomly jumping into a thunk to do evaluation. Okay, and so how do we evaluate a thunk under this model? Well, we just jump to the address of the code that we're going to use to evaluate this thunk, and it eventually returns which constructor it evaluated out to. It has to black hole and do some extra stuff. But this is the key statement. And I don't know how many people have been paying attention to computer science security stuff this year, but this is a really bad statement. So there's been a raft of security vulnerabilities that were discovered at the beginning of the year. There was Meltdown, and there were 2 versions of Spectre, and now they think there's been like 7 or 8 more versions of Spectre found. But this statement right here is vulnerable to the version 2 of Spectre, which is that I can poison your branch prediction table to say, like, at the same address that you have there, something that hashes the same address, I'm going to cause a whole lot of jumps to another piece of your code, anywhere in your process. And then I can get through the speculation buffer. It'll speculatively execute your code at some completely unknown address, and then I can observe through side effects on the other buffers that we have available to us on the CPU. All this, like, whenever you have speculation that your sensor did not allowed to see, you observe whatever you can get out of side effects. We can find out what is other data in your process. So every single thunk in GHC is a Spectre v2 vulnerability, at least to my eyes. And I haven't seen any attempt to seriously address this. This is somewhat concerning to me. And the mitigation for this is a technique called retpo lining. How many people here have heard of this term? Okay, so just a handful. And the idea of retpo lining is to push onto the stack EAX and then ret to it instead of jumping to it. And then it avoids one of the caches on most architectures, except when it's full, and then it goes back to doing exactly what it's doing on modern Skylake. So you're still screwed. And I don't know a fix. I'm not a compiler engineer who's stuck out in the wild fixing these things, but it's been a concern in the back of my brain. So the other problem is that this retpo line fix is rather drastically slower. I've seen numbers like 80% slower. And this pops up in like C++ code that's doing heavy virtual function calls because they do the same pattern. They load a thing out of a vtable and they make a jump. So, but in practice, the mitigations tend to be relatively cheap for Meltdown, but the Spectre costs are going to be with us for a long time. All right. So last year, I gave a talk about SPMD-on-SIMD evaluation as a sort of impromptu replacement for the closing keynote. And in that talk, basically what I was talking about was, if you have wide SIMD units like we do on modern CPUs, I can generally execute 8 integer instructions wide at any given point in time. It makes sense to look at evaluating a function with several copies of its arguments and keeping an execution mask of which lanes are currently active. And so, like, if I go down into an if statement, I will build the mask of, like, let's say I say if x is less than or equal to y, I've got a vector of 8 x's and a vector of 8 y's. I'll do them in one register, I'll do the comparisons. That'll give me a mask. And then if anybody wants to take the true branch of the if, I'll step into the if. And I'll keep track of the execution mask for what portions of the registers I'll clobber and whatnot. Well, if we look at just evaluating combinators, which I have not included on the slides here because then I'd have to build a G machine or something like that in order to evaluate them. What we're going to do is we're going to step in, case analyze on a finite set rather than jump to an unknown address, and then do pointer replacement and keep recursing, right? There's still timing attacks and stuff like that that you could theoretically do, but it is not directly vulnerable to all of these big Spectre jump to an unknown address kind of attacks. And we would get a little bit of extra blinding if your evaluation model was to execute several Combinator reductions at the same time using the SPMD model. And as a side effect, I would be able to execute as many threads as the product of the number of cores I have and the width of my SIMD units. And so in practice with the SPMD-on-SIMD stuff, I find that a lot of the code that I'm running through this pattern, like the Intel SPMD compiler does this stuff today, is about a factor of 6x speed up on the code that I'm interested in running. Like ignoring, like assuming I was already parallel across all my cores, I'm seeing pretty good speed ups. And so being able to say, let's go back to the approach from the 80s, where we've seen there was first a jump of about a factor of 2 to get to Leonard's approach. And then, let's be generous, let's call it a factor of 3 by the time we get through dynamic pointer tagging and all this extra stuff. We get about a factor of 6. Well, if there's another factor of 6 over here on the table, but just by doing it the old way, but on new hardware in parallel, it's rather shocking to me that it's even possible to get into the same ballpark, at least with as little prep work as got me here. So I started from last year, I was talking about this SPMD-on-SIMD evaluation model, and then what I was trying to do was figure out how I could run that through a GHC-style compiler. And I really wasn't making much headway. And so in the end, moving down to a smaller Combinator basis gave me a thing that was coherent enough in control flow that I wasn't frittering away all of my performance by branching too much. And so with a small set of combinators, this actually becomes a viable approach. All right. So I want to go back to that original point that I made, which was that Schoenfinkel's algorithm for compiling from the Lambda calculus down into combinatorial logic blew up my terms by like an O(n) cubed factor. Okay? And I'm going to just kind of try and take away the result from Turner that he's able to do it in O(n) squared. And we're going to see it by looking at what are S, K, and I? What do they mean in terms of plumbing around some kind of environment? And so to me, I view S as like an application. We're applying X to Y. And I'm going to feed each of them an environment Z. Right? So S is really an app cell with a little bit of extra info being passed down. It's one way to think about it. And a K is like, ignore that extra piece of information, the Y, the environment you're being given, and just use this other thing. And then I is, use the environment. Right? It's just get the thing out of this one simple environment. And so once you have that in mind, it becomes immediately obvious why there can be an explosion, or there must be an explosion in terms, or why there is an explosion in the current approach, which is that they all work one variable at a time through an environment. So if you have an environment n symbols long, you have to do kind of O(n) work with k's to throw away the parts of it that you're not looking at. And then the B's and the C, example from earlier, were about just throw it away before you pass it into that branch. It's whether I do X and then YZ, or XZ and then Y. It's just tell me which branch I need to pass it to. And if I don't pass it to either, I can just K the whole expression. I can pull the K all the way up. So this is the general pattern that we follow. If we look at Turner's results, the fact that it's only O(n) squared requires a little bit more administrative work than just this reasoning. But it at least gives a sense of why the problem should be something like O(n) squared. Okay, so I mentioned earlier there was a paper by Broda and another person. If you want some deep results about other attempts to compile the combinators, that's the reference for all the asymptotics that have gone before. So I want to sketch an improved abstraction elimination algorithm and see if we can, I don't have a full implementation of it here for everybody today, but in the world of the Lambda calculus, there's been several attempts or several efforts that actually have been quite successful at implementing a Lambda calculus with a notion of quote unquote explicit substitutions. Tell me the part of the environment that I'm going to push down through this term, but don't do it right now. When I was working with that maybe earlier, it turns out that working with locally nameless representations for the Lambda calculus or de Bruijn indices is particularly slow. You pay for the size of the term to do each one of these like go put in adjust and go take it out. Things that have to happen all over the place administratively in your code. If you want to see a way to reduce the boilerplate on that, see my bound library. It doesn't fix the problem though. Okay, so there's this old paper on explicit substitutions back to the 1990s. There's a good summary paper, which is the second one that I've linked here. And I'll make sure that the slides go out to folks, because I believe I looked at it, and I think I estimated that I average a citation a minute here, so I apologize. And then Francesco Bozzoli, who's a coworker of mine, wrote an article right before I started at Digital Asset on a well-typed suspension calculus, in which he built a version of one of these explicit substitution calculi, but ensured that it was properly typed all the way through. Unfortunately, using the well-typed version that he has costs me asymptotically. So his version is linear time, and the best I can make it is like a log squared slowdown. And the other thing is that none of these actually really address the asymptotic cost of doing it. But I've given talks elsewhere about the bicyclic semigroup. It turns out a nice generalization of that gives us a natural form of explicit substitution. I don't have enough time to really go through it here, but we can build a data type by leaning on Chris Okasaki's work that gets us log time appendable partial environments that can be trimmed in log time and indexed in log time. And so what you now have is, at least in the, like in a real language, you have environments that have kind of a log time indexing. And we could go off and use like a Mogensen, or we could use a Scott encoding of that data type, ensure that we're evaluating our Lambda calculus lazily. There's nothing that says that it has to be, there's no asymptotic explosion in encoding these data types in Combinators directly. And so you could, in theory, take this data type that's written a la Okasaki and ridiculously heavy and build a log time indexable environment, and then use that as the way that we plumb this environment around through our Combinator calculus. It would be a horrific exercise. But it does sketch that there should be an n log n time abstraction elimination algorithm. It's just not natural in any way, shape, or form. And it would rely on the fact that we're doing like outside in normal order reduction, lazy evaluation on the Lambda calculus rather than applicative order evaluation. Okay? But in exchange for that, there seems to be a compilation algorithm for the Lambda calculus to Combinators that would improve upon Turner's algorithm from n squared to n log n. Okay, I leave this as a sketch. It's not a fun exercise, as evidenced by the fact that I haven't finished it by now. But it's also one of those things where, while it looks good asymptotically, it's probably not worth it in practice. So when we moved to supercombinators, what happened was that O(n) squared cost is still there on the stack. Like, I'm dealing with a bunch of variables, and then I'm turning around and copying them down to the next stack frame down. And the expansion of the stack frames that I'm working with can still be on that same order. But now when I go to access them, they're all contiguous memory. Here, I'm going to be doing like a log number of random accesses in memory, a big O of log. So who knows how bad the constant factors are. And so the memory effects would dominate almost any win on any realistic scale of the number of variables you'd be working with. But it's at least interesting that it should exist. So like, an unfortunate side effect of this talk is, by the way, here's several things that all almost work. I'm just warning you. Okay, so this is the first one. The second one is, let's look at another feature of Haskell, which is that back in 1983, as part of his PhD dissertation, John Hughes, on the design and implementation of programming languages, noted that it was impossible for any evaluator that didn't do some concurrent evaluation to avoid certain classes of space leaks in a lazy language. It was one of those, and I'm using lazy versus normal order very loosely. I apologize for anybody who cares. it was impossible to do lazy language as well without some concurrency. And then Wadler came up with a paper a few years later where he said, well, if you just get the garbage collector to do some things like this, if you have a pair of A and B, and you have like first applied to it, the garbage collector, and like the A and B is actually a concrete pair that's been built. The garbage collector should be willing to forward that to an A. And the garbage collector should be willing to forward second. So if you have field selectors applied to a record, and the record's there, the garbage collector should do this work. There's going to be strictly less stuff on the heap after the garbage collector gets done doing its job. And so this doesn't risk termination, but it does mean that if I have a pointer to the first of a pair of A and B, I won't leak the B. Okay? And so whenever anybody turns around and tells me they're going to run a lazy language on a normal language's garbage collector, my first question is always, well, what are you doing about these? And the answer is usually nothing. So be warned. My understanding is that Ada is currently doing nothing in this regard, but like GHC.js gets it right, just as an example. And Frege also, I believe, is doing nothing in this regard. Although it is actually surprisingly difficult to come up with an example other than the one that Hughes used involving breaking large strings where it actually matters in practice. It's still somewhat telling that it's there. So after Wadler wrote his paper on fixing some space leaks, Christina von Dorian, who was a student of Leonard Augustin's, wrote her PhD thesis, I think it was a PhD thesis, on stingy evaluation. Unfortunately, I haven't been able to read it. It's like locked in, unscanned territory in a vault somewhere at Chalmers. So if anybody has an in over at Chalmers, I would love to read the original paper. But the idea, at least from talking to Leonard, is that what we should be willing to do is let the garbage collector shrink the heap. You can view the garbage collector has to copy ON stuff from here to there. You could view that as an amount of fuel to do work, as long as that work results in a smaller heap. Okay. So we could we could teach our garbage collector to do some evaluation for our combinators. So using the vocabulary from earlier, there's a paper by Paul Hudak and David Krantz from '84 where they were using some similar rules to this spirit, like looking for things that would shrink the heap. And they were doing it while they were producing object files. They ran through this compiler for something like SASL. I've forgotten the name of it, unfortunately. APFL something. So it was another functional programming language. And they were compiling down to combinators. And then before they spat out the object files, or as they were constructing these things in the compiler, they would shrink opportunistically or according to a pile of rules. But several of those rules pass my understanding of Christina's test, which is that it doesn't matter what you do, this will always result in a smaller heap. Okay. And then there was another paper from the mid-'80s. There's a lot of '80s references here. Yeah, there's a Ready Player One joke in there somehow. But, which was by a guy named Bill Stoy. And he and a couple of other folks were working on a compiler, on a instruction, or on a microcode for a machine called the SCIM2, which was apparently a hardware implementation of SKI stuff that was active at the time. This is all before I was involved in the world of Haskell and functional programming and what have you. Well, Haskell wasn't there, but in the world of functional programming. I was in 3rd grade. But the idea, he put forth a lot of ideas in this paper from the mid-'80s. And I thought I was super clever to think about like applying this idea of 1-bit reference counting from this paper, or this book I'd read on garbage collection once. And it turns out this was the paper that created 1-bit reference counting. So yeah, I thought I was getting out of my, I thought I had this brilliant idea, and it turns out it was like, why? Because Combinators produce so much garbage. The idea that what we want to do is, if I know I hold the only reference to a thing, I can mutate it in place rather than have to go grab another app cell off the heap. Okay? And so if I look at like S here, if I hold unique references all the way down, then what I could do is I could just in place reuse all 3 of those app cells to build the balanced version of it. But I would have to copy Z because I've now got 2 references to it. So I'd have to flag a bit in the pointer to Z. So this is the idea of 1-bit reference counting. And then if we look at like the rules for C, flip can also be done in place and even return a cell to us as it's working. B, same thing. Const, this was we've already established this one's always safe, even without mutability, or even without reference uniqueness. And so there's a bunch of extra reductions that we can do that would require this extra bit of uniqueness information, or this 1-bit reference count at least, in order to be properly stingy. And sort of the mission that I've had when kind of playing with this is to see if we could get Waddler's rules out of just church encoding my data type. So I can write down first and pair and second, and as combinators, just by running them through the little compiler that we wrote at the beginning of this. And the real question that I have is, can we just get Waddler's rules as an emergent optimization? And I can get pretty close. I can't actually say with 100% certainty that I can get there with the building blocks that I have. The story is a little bit more complicated than shown here because in order to get Turner's rules to fire, I have to actually add a handful of additional combinators I've skipped. Okay. So let's so this is an end goal, or one of several goals of this. I just want Waddler's things to drop out as an emergent phenomenon. The next one here is these are all like a set of observations about combinators in general, is that if you look at the rules for evaluating S, K, and I, and B, and C, and all that stuff, except for Y, if you were to start with a heap that didn't have any cycles in it, you end with a heap after doing a graph reduction anywhere in the heap that still has no cycles in it. Like when we were doing that thing with S, it just balanced a tree. When we were doing similar things with the Ks and the Is, they were just selecting something from below them and lifting it up to replace themselves. But what would happen would be, is if you had a, oh, where did I go? Yeah, there we go. If you started with a heap that had no cycles, if you started with a directed acyclic graph for your heap, you ended with a directed acyclic graph for a heap. This actually opens up all sorts of things. If you look at Erlang's garbage collector, it uses the fact that it has an acyclic heap in order to do it in a single pass. There's been things like in the world of binary decision diagrams, they go through and they use just reference counting because they can naively reference count. Now, I probably couldn't get away with this for something like Haskell because we have IO refs, and we want to have mutable things, and those are going to do cycles. But this opens up the door to considering that we could hash const our entire heap. And this opens up, Ilko Dolstra has done some work on maximal laziness how many people here are Knicks fans? Not the sports team, but yeah. So with his work on speeding up Knicks, it's all been based on the idea that if you have the exact same term floating around in the heap, it should be shared, and therefore doing reductions on it would be shared by everybody. So we could go through and just hash const up our heap. Turns out you can basically borrow the same algorithms that are used for BDDs for this. There's an old paper from Andrew Apple on the topic, which is not on the slide. But why do I care about it? Well, with maximal laziness and with the lazy reference counting, it turns out the dead space in my heap, the spaces I'm not using right now, become memoization table slots. So like if I were to evaluate like naive fib, using the horrible computer science example that all functional programmers go to, then it will turn into the sort of log time, the memoized fib that we would like, or not log time, but the linear time memoized fib that we would like. So why do I particularly care about this problem? This is sort of the last slide I have, which is that I've been working on a compiler for a little toy language. And in that language, whenever you work on a dependently typed language, there's always a sort of series of competing concerns. I have to deal with substitutions on my terms. I have to do unifications on them. I have to evaluate. And then I have to turn around and ideally I have to hash const the terms away so that common terms in my heap of intermediate representations get commented up. And so all of these seem to be things that are addressed pretty handily by this compiling down to Combinators form. And there's a paper by Daniel Doherty from the mid-90s, we've finally gotten out of the 80s, which talks about how to do higher order unification using Combinators. Okay, and this is pretty much the last gasp of anybody I've really been able to find that's done anything interesting in the Combinator world. And so his paper talks about how you can do unification in Combinator form rather than doing unification on syntax trees for the Lambda calculus and whatnot. So with higher order unification, you want to be able to do unification involving Lambdas. And it pops up all over the place in dependently typed programming because you don't want to have to type all of these boilerplate terms. And so higher order pattern unification is used to fill those things in. And so if I can do those things directly on this form, then I don't have to move back and forth by like normalization by evaluation into some value language, make reductions, and then copy everything back over, and then hope I can hash const all of this stuff away and that all the intermediate allocations are gone. Because I can go hand this thing off to my crazy SPMD-on-SIMD evaluator off to the side, evaluate several of these terms at a time. Garbage collector actually is shrinking things, et cetera. It seems to be a coherent vision. And so this has been the general model that I've been exploring for an intermediate representation inside of a compiler for how I'm going to handle my types. I thought it was at least an interesting tour of what are Combinators for folks who haven't seen this before. And it's a laundry list of things that almost work or that seem to have some promising direction by kind of diving through this alternate history. And I think that's about everything I've got. So thank you.